Good morning. My name is George Armistead, and today I'm doing a training video to present some drilling well design and safety best practice recommendations which has served me well in my career. All of these are fundamental recommendations for well design and drilling operations. This video will be posted on YouTube, and the notes and the YouTube video of this session will be posted to my account in Google Drive as well as LinkedIn if you're interested in obtaining a set of the notes used during this presentation. If we look at a simple diagram of a well, with the first string of casing on a deep water well, there are several potential leak paths. The first of which is so if we have a hydrocarbon zone down below the casing here, then the first leak path that we might consider is a leak path up the casing and to the BOP. So if the BOP is leaking, that could be catastrophic failures to have a release that we don't want to have. Another potential place is we could have a leak through the casing itself. So if we've done an improper well design and casing design, then that could be a failure causing a problem. Another one that we typically look at is the cement job itself. So this hydrocarbon bearing zone, we're also dependent upon this cement being a barrier all the way up to the mud line or to the casing string that's above it in which it has been run. And then lastly, we have to think about the earth itself as a barrier, because when we are, when we're drilling this well, we're dependent upon all four of these being barriers or something that we're dependent upon: the BOPs, the casing, the cement, and the earth itself as being barriers to prevent this hydrocarbon bearing zone from getting to the surface. So with this in mind, I'm going to talk about today, not going to talk about casing design. That's pretty well, there's a lot of training that goes on with casing design, and industry does a pretty good job in casing design, and BOPs are heavily regulated. But I'm going to talk quite a bit about the cement job itself, as well as the understanding the rock mechanics in doing our planning. So the next slide I'm going to show is just going to talk about the fundamentals of having knowledge of this rock mechanics. So having rock mechanics fundamental and rock strength understanding is paramount to drilling. Drilling is the operation of mining rock with the potential to encounter very high pressure trapped fluids in the earth from our mining operation. So we have to understand what our rock strength is. So having the skill set to estimate overburden, pore pressures, fracture gradients based on formation types is vital to choosing casing setting depths, determining casing pressure loads, analyzing the integrity of barriers, and doing well control assessments. A well design based only on a shoe test is probably flawed in that the shoe test may have been conducted in the strongest rock type. Drilling engineers should be competent in estimating these values for the areas that they are doing drilling engineering work on, or direct oversight should be utilized until these skill sets are obtained. An analogy of this thought would be an airline pilot or surgeon's qualification requirements. The individual must be deemed qualified for a specific airplane or surgery type and expected to know all of the fundamentals. Knowing the stall speed of an airplane would be an analogy to knowing the fracture gradient when drilling. We cannot imagine that an airline pilot who has been flying back and forth between Philadelphia and Washington, D.C., and then all of a sudden he's assigned to fly an airplane to, let's say, South America somewhere where the altitude is 10,000 feet and land the airplane, and he has been operating in 15 psi environment at sea level in Philadelphia, and now he's going to land a plane in South America at 10,000 feet where the atmospheric pressure is 10 psi, and he doesn't understand what the stall speed is at 10 psi. I hadn't even thought about it. So in our industry, we move people around, drilling engineers around, so a drilling engineer could have been working in an environment only drilling wells with 9 pound per gallon mud, where he never had a problem or an issue dealing with fracture gradients in his environment. And then he gets moved to a geological area which you're dealing with high pressure, high temperature wells, high mud weights, and now all of a sudden fracture gradients is a big deal in understanding well control as well as barriers and many other aspects of a well design. So the most dangerous situation is when you have a drill engineer gets transferred and then his supervisors or manager again has moved from an area in which he has not had to deal with fracture gradients in his career, and now you end up with a situation that could be pretty hazardous situation fundamentally. Our drilling industry has no qualification or certification requirements for drilling engineers, so it's only up to management and supervisors to, instill, I call it, try to encourage training to take place for individuals so that we don't subject them to an environment in which they don't understand their operations. Down at the bottom of this slide, I put some fundamental aspects of it. I'll probably do a future YouTube video talking about fracture gradient, but that would make this one awful long if I did it right now. But fracture gradient is a relationship of effective stress, which is overburden minus pore pressure, times a rock stress coefficient plus the pore pressure. I've rewritten this just with symbols. So fracture pressure is this overburden minus pressure, which is effective stress, times this rock stress coefficient K plus the pore pressure to determine fracture pressure. Overburden is simply the average density of all the layers above some point in the earth that we're interested in. And then the stress coefficient is a ratio of the vertical to horizontal stress. Pore pressure is the pressure within the pore spaces of the rock body. And then effective stress, as I've already said, is a factor, is overburden minus the pore pressure. You can think of it as being the stress that's created from the particles on top of one another as they are stacked. So you always got the pore pressure within those pore spaces, but you also have the stress from the particles touching one another and supporting one another. And then an overburden force upwards is a combination of the effective stress up from the matrix plus the pore pressure. So that's how and having this knowledge is paramount. I mean, we're, like I say, in our world, we're drilling wells, we're mining engineers, so we really need to understand rock mechanics to understand how effective of a barrier our earth is in keeping our well bottled up. All right. The next recommendation I'm going to talk about is to manage. We need to manage cement contamination in order to achieve effective barriers. We've got to use best practice recommendations in order to mitigate the cement contamination effects. I'll first say that if you are a drill engineer working on a well at 4,000 feet in West Texas, you get moved and now you're going to drill a well at 20,000 feet. Just because of the math, the contamination on a 20,000 foot well casing string is going to be 5 times worse than the contamination in cementing a well at 4,000 feet, just because of the math. So we have to do something about it. So in order to do something about it, we have to change our thinking into these kind of recommendations that we need to use something like 30% of the displacement volume of cement slurry whenever possible. Let's say you've been cementing a well in West Texas and only have been using 200 sacks of cement. Okay, let's say 200 sacks of cement was adequate for your condition on a 4,000 foot well. Now you're going to go cement a well at 20,000 feet. you're going to need to use a lot more cement. Just because of the math, the amount of cement slurry is going to increase proportionally to your depth because of your displacement volume. So that's what that means. The second bullet there is to use appropriate wiper plug systems for your type cement job. So you should always use 2 wiper plug systems for casing strings and 4 wiper plug systems for liners. The wiper plugs separate the cement slurry from the mud and aids in getting much better displacement as well as managing contamination. We also need to use centralization best practices. There's a lot of information by industry about centralization best practices. We should incorporate them. Avoiding using centralizers is not the right answer. We need to use them appropriately. And then the very last one is we need to use a minimum of a 1.5% chute track volume based on displacement and incorporate critical thinking into the decision making, even to increase that volume when it's appropriate. As an example, I just did the math that if we left a 1/16 film of mud on the casing wall behind the front wiper plug, these volumes that are shown on the bottom would be the percent volume of contamination that would be picked up by the second wiper plug as it wipes that casing wall going back down through the casing again. So you'll see that as we go down in size, the percent volume of contamination increases. So for 13 3/8 casing with a 12 3/8 ID, that percentage would be about 2%. For 9 5/8 casing with an 8 5/8 ID, the percent contamination could be in the order of about 2.9%. And then for 7-inch casing with a 6 1/8 ID, the contamination volume percent could be about 4%. So let's look at an example of this that as we're doing a cement job, what we expect and what might be happening. So the diagram on the left is kind of what we think about every day is happening on our well bores. We have a 10,000 foot well, and someone has chosen 3 chute track joints as being adequate. Casing has an 8 5/8 ID, and they show a diagram, a perfectly cemented well, no mud residue left on the casing wall behind the front wiper plug. Got a pristine cement job below the wiper plugs and outside the casing. But what really probably happens, majority of our wells we drill today, we're drilling these wells with oil-based mud. So when we run the casing gets oil wet. And then we pump water-based cement slurry down through that casing to do the cement job. So if we thought this 3 shoe joints were just adequate for this well, and we do end up with a 1/16 film on this well behind the front wiper plug, and we do this job as being executed, and that second wiper plug scrapes the wall and picks up this volume that's left on the casing wall, that volume is 2.9%. And so here's the math for you to see the 2.9%. So 2.9% of 10,000 feet is 290 feet. But we only have a 130 foot chute track. So we're gonna fill up. What's really gonna happen is we're gonna fill up the entire chute track volume with contaminated cement, plus have contaminated cement on the outside of it. So that's what we will end up with if we don't do anything to mitigate it. So the right solution, if you think about this and use critical thinking, and you do think 1/16 of an inch is a realistic amount of film that's left on your casing wall, a potential solution would be to use a longer chute track. So a longer chute track would be, say, 400 foot chute track, which is 4% volume, and that would be long enough to catch all of this contaminated volume, which is 2.9% contaminated volume that is picked up by this second wiper plug, and it leaves it in the upper portion of the shoe track, and you have high quality cement in the bottom part of the shoe track as well as the outside of the casing. Really critical idea. All right, let's look at a case just in case that we might think about it. Is this important enough? So I've already described, hope you'll remember these numbers, that the minimum slurry volume should be around 30% of displacement volume, if at all possible. And then the recommended shoe track volume, the minimum should be about 1.5%. Let's take a look at an example in which the slurry volume was approximately 7% versus 30%, and that the shoe track volume, instead of being 1.5%, it was only 0.9%. You say, well, it doesn't really matter. Nobody really cares. Well, it may matter an awful lot. Here's a case picture after that was done. So, you can make your own determination. Is doing a good cement job and managing contamination important enough to pump a lot of cement and use a long shoe track such that you manage contamination? It's a big battle. We can mix up and do lab tests on cement slurries in Warren blenders at the surface and do a perfect job of having very good high quality cement slurry. But then when you take that and you pump it down through 20+ thousand feet of casing and through all the lines on the rig and whatnot, you want to have high quality cement in place when you stop pumping. And you want the cement to be high quality at the bottom of the well, not in a Warren blender in the office. So that's what we're trying to accomplish. All right. Okay. All right. The next recommendation I'm going to talk about is to mitigate the pressure transition effects of cement slurry hydrostatic during the curing process. So it's very important. This has been well known since the 1960s, as cement slurry goes from a mixed slurry of water, cement, and other additives with the particles suspended in a solid form. There is a period of time in which the solids support themselves on top of each other, leaving the mixing water as the hydrostatic pressure in the cement column, which reduces the overall wellbore hydrostatic in the cement column section of the well. And also, another kind of recommendation that goes along with this cement process is that we need to verify the integrity of cement as a barrier by testing it before we ever remove any BOP equipment. And a practice that I adopted a long time ago that has served me really well is to never monitor a well with the well bore open. There's a lot of times when we call it monitoring wells or waiting on cement, but my idea is that if we are watching a well bore for some possible event that is going to be bad, then don't watch it at all with it open. Close in and secure the well and record the pressure in time increments where nothing bad can happen, rather than reacting to a negative event and then trying to secure the well. So it's, for the most part, we can always shut the well in and then just write down pressures in a pipe book rather than watching for something to happen and then trying to close the well in. So this idea is particularly applicable for after doing cement jobs. And then a corollary to this whole process about waiting on cement afterwards is to always be rigged up before beginning a cementing or other operation to do whatever is necessary, such as draining a stack, riser, or washing out excess cement without having to disconnect equipment. You should always be rigged up to not have to disconnect your equipment to wash out the well. So this is a very important principle. Let's look at an example of this, of transition effect. Here's a diagram of a well that I just made up. This is not a real well here, but I made up a well at 10,000 feet. in which we have a hydrocarbon bearing zone at 9,500 feet that has an estimated pore pressure of 11.5 pounds per gallon. If we start with this in mind, the pore pressure in that zone is about 5681 psi. Well, if we drilled a well with 12 pound per gallon mud, we don't have any problem with our mud because our hydrostatic from drilling of the well is 5928 down to this zone, which is 248 psi overbalanced. Our hydrostatic pressure of the mud is greater than our hydrostatic pressure within the zone. No problem. But we encounter this zone, we drill through it, we log the well, we run our casing because we want to make a completion, and so we do a cement job. So let's assume if we cemented this well up to 7,000 feet, which would not be unusual, I call it, we end up with 7,000 foot of mud hydrostatic column down to some place in the well, and then we end up with 2,500 feet of mixing water. This has been well known since, like say, about the 1960s sometime as being hydrostatic for a period of time. That period of time may be short, but it does occur. So in this case, the mud hydrostatic is 4368. The 2,500 feet of mixing water is 1,079. You add these two together, we end up with a hydrostatic at the top of the zone of 5447, which is less than the hydrostatic pressure within the zone. So during this period of time, the well goes underbalanced by 234 psi. And the funny thing about this is there's nothing wrong. There is absolutely nothing wrong. The thing that is important to know is that as your pore pressure of your zones increase above 8.3 pounds per gallon, which is what mixing water is, this condition gets worse and worse and worse. So it's much worse if the pore pressure is 15 pounds per gallon than it is if the pore pressure in this zone was 9 pounds per gallon. So as the pore pressure gets worse, then you got to do a better job of managing this as you go along. Let's look at a real case. So here's a real life case that I pulled off of public information that actually occurred. And on this example, we've got a well that's at 1,700 feet. It's only 1,700 feet in the Gulf of Mexico. And they had two hydrocarbon bearing zones in this well. One was at 710 feet and one was the 1,170 foot sand, which had 499 psi bottom hole pressure. The well was drilled with 9.4 pound per gallon mud and cemented with 11.4 pound per gallon cement slurry. You would think the top zone here, if you look at it at 710 foot, has equivalent mud weight in that zone if you calculate it to the surface of 7 pounds per gallon. And if you calculate what the pore pressure is in that zone, once you've drained your riser down to the plus 10 valve, which was 113 feet, the equivalent weight then was 8.4 pounds per gallon up to the plus 10 valve. The lower zone had an equivalent mud weight to the surface of 8.2 pounds per gallon and to the, I call it the plus 10 valve of 9.1 pounds per gallon. So in this case, they drill the well, they drain the upper part of the riser down to the plus 10 valve because they're drilling a well over a platform. They don't do anything about it, and the hydrostatic drops in this case while it's going through the transition period to the plus 10 valve, it drops to an equivalent mud weight, which is 257 psi, which is 3 psi underbalanced to the pressure in the upper zone. The bottom zone drops to an equivalent pressure of 456 psi, which is 43 psi underbalanced to the bottom zone. They say, well, that's awful close. That should not make any difference. Let's look at like a picture while we're waiting on cement. What that looks like, operation looks like while we're waiting on cement. Here's the rig that has caught on fire, burned down the platform. The derrick is laid over the platform. You can say, why didn't we shut the well in and secure the well while we were waiting on cement? I mean, how easy can it get more than this, a 1,700-foot well that's normal pressured? So there's nothing wrong or unusual about the geology or the well conditions. The pressure transition effect has been well known since the 1960s. Cause failure to maintain hydrostatic pressure and a secured well throughout the entire setting process of cement slurry. Lack of prevention measures. The mentality people use, it hasn't happened before, so it's not going to happen to me. That seems to be our tactic. It's just to say it's not going to happen to me. And that's not much of a tactic. As always, I've said, always monitor well, if possible, with it closed in and secured. Write down the pressure on a gauge every 15 minutes rather than watching for something bad to happen and then reacting. It's fairly easy to, like I say, to mitigate this effect. All right. Now, many years ago, I came up with a system that I'll just say this real quickly. A lot of times as drilling engineers, we don't want to be waiting. So we don't want to be waiting. If we can avoid waiting with our BOPs closed, we feel like we're not doing anything. So a system that I came up with years ago for a wellhead system was have a base plate that has an outlet on a base plate and a wellhead installed above this plate, such that when I drill the well, I install this whole assembly on top of drive pipe offshore, and I can drill the conductor hole and then run this orange piece as the hanger for the conductor casing. It has seals on it that seals off in that plate and take returns to a valve that's put on the outside of this plate. So the well is secured after I cement the conductor casing. Likewise, I drill the next hole section below the conductor casing, the surface hole. I run surface casing and I hang the surface casing off in this wellhead housing, and I take returns through this valve, these two valves, which are installed outside of it. And once I land that casing hanger in here, the hanger seals off through the inside, the valves are closed, and the well is secure. So there's a lot of things that you can do if you want to speed up your operation by just a little unique designs, incorporate that into your planning. All right. All right. The next recommendation I'm going to go over is to know your operational requirements for all rig types, as well as the best practice operational considerations. So some examples of these, I'll go over each of them. The first one is to follow hatch closure procedures during all mobilization operations of all floating type rigs, including barges, jackups, submersibles, semi-submersibles, and drill ships. Buoyancy is a wonderful gift of science, but we can have very serious consequences when we ignore or take it for granted. We've got to close those hatches. If you get into a bad weather condition and it starts taking on water through hatches that's left over, next thing you know, the rig's listing and it gets worse and worse and worse, taking on more water faster, and the next thing you know, the rig sinks. So, bad idea. Second one here is to mitigate leg punch through during the preloading of the legs on an independent leg jackup rig by preloading with a minimum air gap between the rig barge and the water. Very, very important recommendation here as well. So if you take a look at a independent leg jackup rig from the top view, you have 3 legs on an independent leg rig that are spaced out. So that's the top view. And if we look at the same rig from the side, Here's the rig view from the side. So when we jack up the rig, in order to preload a rig, you want to barely jack the barge up above the water. Because to preload a rig, what we're doing is we're pumping water into compartments in the barge, driving these legs down in the earth to get support from the soil conditions to support the maximum load that this rig will ever encounter when drilling a well. Well, if we are a long way out of the water, and while during this preloading operation, sometimes a leg will encounter a soft place due to soil conditions, and it starts going down fairly fast. We call that punch through. If it happens, we want the barge, this air gap, to be very minimum, just a very few feet, such that the barge goes in the water quickly, and you get the buoyancy back from the barge to keep the leg from going down. If you're a long way out of the water, there's nothing to keep this leg from going down, and then you end up putting a bending moment on this leg through this housing, jacking housing, and you can either bend the leg or break the leg off and cause a catastrophic, I call it the structural collapse of the rig. And here's kind of a picture of what, if you don't pay attention to punch through, this is what you can end up with. Here's a case where it probably wasn't mitigated very well, and the leg starts going down, breaks a leg off or bends it, and next thing you know, the rig capsizes, and then a hatch is probably open, and then the rig ends up sinking. So, I mean, this is a very easy condition to manage if you mitigate it by doing it barely out of the water, so that you get that buoyancy back. As soon as that barge gets in the water, you get the buoyancy back, the leg quits going down, and then you can start all over with the preloading process. All right. The next recommendation that I had for us to take a look at was where is it? All right. To mitigate scouring underneath bottom supported rigs such as barges or submersibles in the planning phase if in operational areas with currents. So if you're drilling a well along the, say, Gulf Coast of the U.S., that you're outboard of river systems like the Chafalaya River, Mississippi River, you can have some pretty good currents coming along the coastlines, and you need to mitigate that. So one possible solution is to place the rig in a purposely dredged hole below the normal ground elevation to allow gravity to mitigate scouring underneath the rig. So here's an example that I drew. I'm not a very good artist, but I think this explains it well. So if you don't pay attention to this problem, if you set a barge just on the bottom and you have currents, you can end up having currents which leaches out the soil under a portion of the rig. I've had cases where a diver could walk entirely underneath the rig in places. Makes the rig very unstable, starts rocking. That's not a condition you want to drill a well. So the best solution that I've came up with is to actually dredge a hole, say 5-7 feet down below the normal mud line, put a couple of feet of limestone in the bottom of it, place the barge under the mud line by 5 feet or so. Then you allow gravity to keep, as scouring tries to take place, gravity is a wonderful thing as well. Gravity fills up anything as scouring tries to take place. You constantly having sediments falling in from gravity from other places as sediments are moving around. Keeps it full, keeps the well stable. So it's a really good idea if you're dealing with this kind of a problem. All right, then have just a few more recommendations to go over. The first one is to always purge surface equipment, tanks, separators, etc., with nitrogen before any flowback or test operation. Small amounts of H2S, from the flowback stream reacting with rust on the surface equipment causes spontaneous combustion. And if you have the presence of hydrocarbon anywhere in the system and left in a tank or anything like that, can cause a fire or explosion. So always make sure you don't have a combustible mixture by purging it with nitrogen. Okay, best solution. Second one here is to mitigate hydrates when conducting pressure bleed-offs across all valves or pressure equipment on high pressure, high temperature wells. When you bleed off with a very small leak across a valve, it can form hydrates. So hydrates is one of those kind of exceptional products in the world of physical chemistry. And so it's a solid. It could be a solid at a fairly high temperature. So prevention is much easier than reacting to hydrates once formed. The solution is to spot glycol across equipment to prevent hydrates and methanol to remove hydrates. So I'll give you an example. Let's say you've just completed a high pressure, high temperature gas well. And in order to secure the well and move the rig off location, you're going to close the downhole subsurface safety valve and bleed off across the valve. Well, we always want the subsurface safety valve to be holding, but if it barely leaks, you could form hydrates. So in order to prevent this from occurring, is you close the downhole subsurface safety valve, pump 2 or 3 barrels of glycol on top of it, then bleed off. And then at the surface, normally one of the last steps we always do is to set a back pressure valve and bleed off across a back pressure valve. So doing the same thing, you would set a back pressure with some well pressure on the well, pump a barrel or 2 of glycol on top of a back pressure valve, then bleed it off. That way you won't form any hydrates on top of either the subsurface safety valve or the back pressure valve during the bleed off periods. And then the very last one here is to avoid closing a downhole subsurface safety valve with solids laden fluid across the valve, if at all possible, to prevent from getting solids behind the flapper, causing it to prematurely fail. So on a subsurface safety valve, you've got the flapper down here at the bottom that's on the outside of a flow tube. And so when you run this in the well, you want to avoid, many wells I have drilled, we completed the wells with solids laden fluid, oil-based mud that was 17, 18 pounds per gallon oil-based mud. So the trick is to never close it with the solid laden fluid inside of the valve, because if you close this valve with heavyweight oil-based mud that's got solids in it, these solids get behind this flapper in this mechanical mechanism and around the flapper, and it may prematurely fail in a year or 2 after you've completed a well. So the trick is to if you run the valve in oil-based mud, before you close it, displace clear fluids through the valve, and so you don't have any solids laden fluid inside this valve when you close it. So both of these are really good suggestions. So I hope you have found this video very helpful for you to understand some of the critical aspects of well design and drilling operations that will make your operations safer. Good luck to you in conducting your drilling operations. And if you have any questions or comments, my email is on the slides, so you can email me if you have a question. Also, you can get a copy of the slides that I'm going to post on Google Drive as well as my LinkedIn account. So I've enjoyed doing this. I hope if this can keep one event from occurring in our industry, then it's been well worth my time doing this video. I've enjoyed doing it, and have a great day. Thanks.